Hey people! Have you had it with all this math stuff? Would you rather be spending your time doing something totally different? Yeah, I hear you. I feel the same way sometimes. But hey, just to make things a bit more bearable for you, we're going to go ahead and show you how you can figure out forces using just a ruler and a pencil. Let's go! So we should all know what a force is by now. Or I hope so. At least when it's being shown as a vector, a force often looks something like this. On a 2D plane, a force like this one has two components, an x component and a y component. And you might also know already that for all the forces to be in equilibrium, the sum of the forces has to be 0. But instead of dealing with all these nasty summation symbols, we can also use a graphical method to show force equilibrium. Prepare to have your mind blown. So here's a quick example. Let's take a cheap example, like this mess-up egghead version of Mona Lisa right here. A picture's hanging on a wall supported by nothing but a thin string. The downward force exerted by the weight of the picture is 40N. Now if we take a mathematical approach, the first thing we're going to do is cut the knot where the ends of the string meet and the picture is hanging from. Now it looks like this. We set up the equations for force equilibrium in the x and y directions, and we get something like this. Since we know alpha and Fg, we can use this to determine the forces exerted by the strings S1 and S2. Then we easily get this result for S1 and S2. Yep, we sure know how to do it that way, but let's try to solve the problem without any algebra for once. For force equilibrium, the same thing applies here. The sum of all the forces has to equal 0. But how do you draw something like that? Real easy, actually. If you take all the forces in play and line them up one after the other, you should be able to get back to the beginning. For any given node, it could look like this, for example. If all the forces acting at the node are in equilibrium, then it needs to be possible to arrange the forces like the image on the right. If you end back at the same place you started, you've got an equilibrium. Let's try this out on our example from earlier. Now before we can solve this using the graphical method, we've got to decide on a length to give Fg. Since Fg has a value of 40 Newton, 4 centimeters seems about right. That would be 1 centimeter for every 10 Newton. I mean, we could also make it 1 centimeter equals 5 Newton to make a bigger diagram and allow for more precise measurements with the ruler, but let's just stick with 1 centimeter equals 10 Newton for now. So the first thing we can do is draw Fg with a length of 4 centimeters. Unfortunately, we don't know the lengths of S1 and S2 yet, but we do know their angle. So for now, we're going to draw their lines of action only. Starting with S1. S1 makes an angle of 40 degrees with the x-axis, so we draw a slanted line of action through the tip of our Fg vector. And for S2, we know it's slanted at a 40-degree angle to the x-axis as well. The trick is that we want to reach a force equilibrium, which means that all the forces have to lead back to the starting point. So the line of action for S2 needs to lead right back through the point we started from. And that's it. The lines of actions intersect one another, so now we know where the force for S1 ends up and where the force for S2 begins. And since we are so mind-bogglingly precise with our drawing, now we can just use the ruler to measure the magnitude of the forces. So when we started, we said 1 centimeter equals 10 Newton, in which case 3.1 centimeters equals 31 Newton, which is pretty much what we got when we solved the problem using math. Well, that's that then. Okay, let's go over everything one more time. We first choose a scale that makes sense for the size we want our drawing to be. If you drop the ball here and it ends up being so tiny that you need a microscope to see it, you won't be able to measure a damn thing with the ruler at the end. So think about the scale you want to use before you start, then think about it again. Base your scale on your largest force and go from there. And the second thing we have to remember to do is to draw the lines of action for the unknown forces. When you have two unknown forces, one line of action should run through the tip of the last force vector, and the other line of action should run right through the point you started from. So guys, this graphical method is easy to learn, and it can really help you rack up points on the test. And if you want to make sure no tester will ever get the best of you, give our practice problems a go beforehand, and everything will go as smooth as melted butter. So take care and have at it.